Welcome back everybody to my fourth GLSL tutorial, and in this video I am going to talk to you about the per-fragment lighting or per-pixel lighting as you like to call it. And this is a little bit bigger subject than the previous one, but the first actual useful subject, because this is the first subject in this series which you cannot just simply accomplish with the fixed functionality of OpenGL. Because whenever you use OpenGL, you pretty much apply the color calculation per vertex based. That's pretty much mean if you have a polygon like this, then you pretty much apply the color calculation to this vertex, so the first vertex, the second, third and fourth vertex, and then just using interpolation to get the value which you want. And that's kind of okay if you have a model with a lot of polygon. But if you just have, for example, this quad right here, for example, which we have in our example right now, because if I run it, it's exactly the same as last time, as you can see, just a simple quad. But the fixed functionality, it will be just for color calculation, and it will be very ugly. Mostly features like specular lighting will be the most ugliest amongst all. Okay, so that was just what I want to talk about quickly. So let me go through these ideas. So the first important concept about lighting actually is that the output color is actually equal to the light color times the material color, where the multiplication is component wise. So you multiply the R components in the light and the material, the green components in the light and in the material, and similarly with the blue. And that's because, for example, in case of a white light, the white light containing three kind of colors, so red, green and blue. Of course, in real life it is a little bit different, but similarly it contains all of the possible colors. And the green material is green because it absorbs the blue and the red light and only reflects the green light. So basically, OpenGL using a floating point number between 0 and 1 to store both the color value of each component, both the material value for each component. Basically, you can interpret it as percentages. So how many percent of the incoming color will be reflected, basically. For example, if 0.5 is the value, for example, for green, that means that 0.5 will be absorbed and 0.5 will be reflected. So if 50% of 0.5 is the incoming color, 0.5 will be absorbed, then reflected will be 0.25. It's kind of obvious, I think, just thought I would make a deal about this subject as well. The second is a little bit about the vectors. It's actually more precisely the dot product. The dot product between two normalized vectors is actually giving the cosine of the angle between the two. So here is an example. Here is the vector 1, here is the vector 2. And if these two vectors are normalized and I use the dot product basically multiplying together the corresponding components, so the x components plus the y components plus the z components of both vectors, and that will be the result. And basically this will give the cosine of the angle between the two vertices. And of course you can get the actual angle by using the inverse operation of cosine, which is a cos or arcus cosine, a cos in C++. Okay, so for example, here is two vectors which pointing to the exact same direction, so 0, 0, 1 vector. And if I get the dot product between them, 0 times 0 is 0, 0 times 0 is 0, 1 times 1 is 1, adding these together is 1. The arcus cosine, so the inverse operation of cosine, we can see that this is 0 degrees, and indeed, because they are pointing in the same direction. Now try another vector, so I have a vector which pointing up, pointing on the x-axis, so like this. This is one vector, as you can see, 1, 0, 0. Then I have another vector which pointing upward in the y direction, so this is looking like this. And if I do the dot product between them, 1 times 0, 0, 0 times 1 is 0, and 0 times 0 is 0, so the result is 0 after adding this together. And the arcus cosine of 0 is actually 90. So, and indeed it's 90 degrees between these two vectors. So as you can see, it works for these two examples. And of course it works all other examples as well. Just I thought I would make two obvious examples right here to demonstrate to you that this is actually working. I would not go into the mathematical part why it is working, but it's working. The important thing is that you should always normalize the vector before you add them to the dot product. Okay, and I just draw here the function of the cosine, so this is how it is look like. I will refer to it later on. Okay, and let's go to what kind of different light there are. Of course, you already know if you have watched my OpenGL tutorial about the fixed functionality. There is ambient, diffuse, and specular light. So let's see how these are made. So the ambient light is everywhere. So according to the definition, it's everywhere basically. And basically this tries to mimic the real life situation where a lot of small lights from every direction and a lot of reflections basically create a solid color everywhere in the room, even the darkest room, and so on. So to make that, we just simple for every single fragment, for every single pixel, we add the color of the ambient light. Don't forget that the output color is the material color times the light color. So the light has an ambient property, the material has an ambient property, so we multiply these together component-wisely, and that will be our ambient property. This was the simplest kind of lighting. The next is actually a little bit more complicated, the diffuse light. The diffuse light is basically this light right here, which this red arrow pointing at. So it is brighter where the light is actually perpendicular to the surface. So for example, here in this case, this is the light source right here. In this case, it is almost at maximum because here the vector to the light source is almost parallel to the vector, the normal vector of the surface. So here it is, for example, a little sphere, and you probably know if the light source up here, then this first part, this first vertex is actually, this first polygon rather, is almost at maximum lighting because this light is parallel to this surface. And then this one gets a little bit less, and this is almost parallel to the light. So in that case, the two vectors are actually perpendicular, but to the surface, the light vector is parallel. So it basically gets no lighting. You can easily try out yourself, get a flashlight, and try to use another, I don't know, material or surface. And as you rotate the light, the less and less light that surface which you try, I don't know, table or for example, will get. So this is the basic idea. And whenever you almost hold your flashlight parallel to the surface, basically the surface gets no light at all, or some very minor light. But in case of OpenGL, it will get no light because the light comes like this and the surface is like this. So they are going obviously, so they are not getting any light. Okay, and here in this case, let me just do it back. So in this case, as you can see, the normal vector is more than 90 degrees from the light vector, because the light vector is something like this. And in that case, according to the definition, there is no light there because the light comes like this and actually not go through the material but stops right there. So it gets basically no light, similarly to all other faces and all other pixels which is under the light, which is basically on the back side, because the light cannot shine through the back of the face, obviously. Okay, to actually get that, we use the dot product, so it will define basically how many percentage of the light comes perpendicular. Yeah, so the dot product between the normal and the vector which pointing to the light. To get a vector which points to somewhere from a point, we just simple subtract the start point from the end point. This is how we can get a vector which pointing to somewhere. So we get the light position vector. I will call it vec to light or something, surface to light, I believe that's what I will call in the program, never mind what you call it. And then you do the dot product between the normal. If the two is almost parallel, so the two vector is almost parallel, then it will basically give 1 as the result. So let me go back here. Here is the example when the two is almost equal. Actually, in this case, it is equal. Oops, again, bad surface. Here, it is it. So as you can see, if the two vectors are almost equal, so the vector to the light and the normal vector are almost equal, meaning that the light is actually perpendicular to the surface, this will give back 1. And as we go, as you can see, it gives smaller and smaller values. Basically, we follow the path of the cosine function. So here it is 1, and then slightly go to 0. This, in case if it is 0, like here, then it is 90 degree basically. This is 90 degree. So in that case, it is 0, this contribution, so the result of the dot product. And indeed, if, as I said, if the light is actually parallel, the light direction is parallel to the surface direction or the phase direction, then basically we get no light. If it is perpendicular, then we get the maximum light. And between them, according to the function, we get smaller and smaller values. This is the basic idea of the diffuse light. One important thing is that if this is less than 0, so the dot product is less than 0, that pretty much means that the normal vector is more than 90 degrees from the light vector. For example, this case right here. And in that case, we basically get no light according to the definition, because as I said, the light doesn't shine through the material, so it will stop, and the front side doesn't get light if it is not facing to the light source, obviously. So this is the basic idea. We just get the cosine function and use that, and it will be stored in a float contribution variable. And we'll multiply this contribution variable by the out light of the diffuse. So again, don't forget that the output light is the input material color times the input light, and that will be the output color. I multiply with the contribution, which is in case of 1, so it is perpendicular to the surface. Then I get the maximum possible diffuse light. If it is parallel, then I will. So if the light is parallel to the surface, then I get no. Then I get obviously no diffuse light at all. So in this case, as you can see here, somewhere the light is here. As you can see, it shines right here, and here where it shines, it is the brightest. And as we go, it basically gets not that shiny, so it gets blacker basically. And here, it's probably here at 90 degrees. It basically gets no diffuse light at all. Oh, the last one is the specular light, which is basically this dot right here, this shiny dot. And that is a little bit more complicated, and I think it is more interesting as well. So what I do is get the vector to the light position. It's very simple. We already did that. To get the vector to the light position, we just subtract the end position from the start position from the end position. Oh, and by the way, one thing I forget to mention, all of these vectors will be normalized because the dot product weighting them normalized in order to the calculation be correct. Okay, we get the normal vector. That's pretty simple. Again, we need a vector player position, which is pointing to the player. To get a vector which pointing to the player, again, very simple. Just subtract the start position from the end position, where the end position is basically the player, which is 0, 0, 0 position, because in OpenGL the viewer is always at 0, 0, 0 coordinate. And again, remember that in order to seem that we are moving, we move everything in the opposite direction. So actually this player position is just the negative of the position, and we normalize it. Okay, this reflection vector is actually pretty simple. It's a built-in function into GLSL. And it's basically waiting for the light position, the normal vector, and it will give back this vector right here. Actually, it will not give back this vector, but give back the vector which pointing to the opposite direction, because GLSL waiting so that you give the vector like this. So input vector and then normal position like that, normal position, and it will give back the reflection of this vector. So it will give back this one right here, as you can see. Although we have the light position actually pointing to the opposite direction, so if you put a negative sign into the light position or before the reflect, it doesn't matter which one, you will get back this vector right here, which is the reflection. Okay, and the last one is actually the actually I said already the player position. So the thing which we have to do is use the dot product again and dot together the reflection vector and the player position. It will basically get how far away from the light reflection are you. So it's obvious that if you look directly into the reflection, you will see this point. But as you are here, for example, not directly looking at, you will see a smaller reflection. Basically, that's the idea right here. So in order to do that, we dot together, so get the angle. Again, if the two vectors are parallel, we get a number 1 in this case. And as we go farther away, we get smaller and smaller numbers. So we get the contribution. The problem right here, although this works, and this is what we have to do, dot together the reflection and the player position vector, that it will be a huge point. It will not be a small shiny point like right here. As you can see, it's a relatively small point, but it will be a very shiny point. It would be like this one, so this entire sphere would be a reflection. And that's because if I open up the calculator, so if you get the cosine of 50, we still get 0.64 contribution, which is very big. It's still more than half of the contribution of the specular. We don't want that. We want that a small shiny point there. And in order to achieve that, we will use the power. So we get the power of something. So for example, get the power of 10 from this number. In order to get the power of 10, we will use the power function, POW. And now if I calculate it, as you can see, I get a very small number which is close to 0. But if I have a higher contribution like 0.9999 and get the power of 10 from the 0.9999, as you can see, I get a number fairly close to 1. And this is exactly the point. If we're looking directly at the light, then we get a very high number, close to 1. And if we get the power of that number to some power, in this case this is the shininess, this is actually the same variable as you would set in the fixed functionality with the shininess. And if it is close to 1, it will remain close to 1 after this power function. But if it is farther away from 1, again, if I have a number like 0.5 and I get the 10th power of that, I will get a number which is almost 0. And this is exactly what we want to achieve. Here, where we are almost directly looking at the light, we get a number close to 1. After the powering function, it will still be close to 1. And as we get farther, we get basically a number farther away from 1, for example 0.5. And after the power function, it will be almost 0. That is the whole point in the specular light. It may seem complicated for now, but keep watching and probably it will be a little bit simpler in the code because there is a lot of theory right here. So let me go back to the code and actually let's start the coding because that's where the interesting stuff are. Okay, here I have the exact same program as I had last time, but actually I don't want it right now like this because I don't want to care about texturing and so on. By the way, to do texturing, it's just as simple as get the material color ambient and the material color diffuse to the current text color, so the current pixel color of the image. But as I said, I will just use simple materials for now. I will not use texturing, but it's pretty simple to rewrite it to texturing. So I get a vector 4 and for now just make it a red quad. Okay, and let me actually delete these sampler things in here. What else? Actually delete everything from here. From the fragment shader we will rewrite everything. In the vertex shader pretty much everything can go again. So delete everything, only the GL position will remain for now and we will rewrite it. In the main program this GL uniform can go and I think most other things can remain. Actually these cannot. Now it's okay, I deleted everything and if I would compile this program right now, which I am currently doing, and run this, we will get the same result as in the first tutorial I believe. As you can see, a red quad without a compile error, so as you can see I have no compile error. And yeah, that's pretty much it. So I believe we are ready to start. In the vertex shader there are just not too much modification which we have to do because most of the stuff is in the fragment shader, because as I said we're doing a per-fragment lighting, not per-pixel lighting, per-vertex lighting, because if we will do a per-vertex lighting every calculation will be in the vertex shader right here. But as I said, we are doing per-vertex based lighting, so we put everything into the fragment shader because we want it to be applied every single pixel. In the vertex shader we have to create two varying variables, so let me create two varying variables, varying vector 3, and I call this one position, and then make another one, varying vector 3, and I call it normal. Okay, the normal is obvious what it is, the position is not so much. It is always almost the same as GL position, except I will not do the multiplication with GL model view projection matrix, just the GL model view matrix, because GL model view projection matrix try to project your point according to the GLU perspective, so whatever you give there. We don't want that, we just want the current position of every single vertex in our, so every single vertex. We don't want to care about projecting the vertices into the position so that it could be used for rasterization. We just want the position in 3D space, and to get the position in 3D space I will use the GL model view matrix without the projection. That is another built-in variable, so let me immediately make that position, and this is equal to the GL model view matrix times the position. Although here there is a problem, GL model view matrix is actually a 4x4 matrix, while the position is actually a vector 3, as you can see. So what I'm going to do is convert this, actually not a position, what am I writing? This is the GL underscore vertex. That's right, we don't have to so we don't have to do anything, we can make this multiplication. So I get the incoming vertex position multiplied by the model view matrix, so we get what we get after the translation, rotation and scaling, what position, and then I have to convert this to a vector 3. So vector 3, I can make it like a vector 3, or I can get the x, y, z components from the result. Either way it will work, so the position will be actually the position of the vertex without projecting. The normal is basically the normal vector, so let's make the normal equal to the GL underscore normal matrix. This is another built-in variable. The normal matrix is actually the inverse transpose of the model view matrix. This is a very ugly word, so I really shouldn't use this. But basically what the normal matrix is, if you rotate the model, obviously you want the normals to be rotated. But for example, if you translate the object, you don't want the normals to be translated as well. So that's why we have matrix for the normal as well, not just for the model view, because you don't want the translation, for example, to get effect on the normals. You want the normals to be stay at normal space. That's basically it. So anyway, basically whenever you want to handle normals, you just use the GL underscore normal matrix always, and you multiply the GL underscore normal variable for that. This is again a built-in variable, the GL normal, and whenever you do something like GL normal free f, and you pass that like 0.0, 0.0, 1.0, this is the current normal vector for this quad, then basically it will be in the GL normal. And the GL normal matrix, this is, by the way, this is a vector free, and this is a 3x3 matrix, the normal matrix, not a 4x4 matrix, because there is no need to translate the normal matrix. Okay, and actually this was all the modification in the vertex shader. So again, get the position, and the position is basically after what we have after translation, rotation, and scaling. And get the normal. The normal is basically the normal vector, just we multiply by GL normal matrix. That's pretty much it. So let me go to the fragment shader, because that's where all the magic happens. So I will copy these varying variables, and pretty much we need a lot of variable for both the light color, both the ambient, diffuse, and specular, both the material, ambient, diffuse, and specular. This is a lot of variable. I believe it's 6, but we need one more, that's 7. So let me create them immediately. I will decided that I will use uniform variable to give that to the program for now. So I will use caps lock, uniform, and this will be a vector free, and just ambient. So this is ambient. So this is the material ambient property. So this is basically the same kind of variable which you will set with GL material FV and GL ambient. So by the way, there is a built-in constant called GL underscore front material, which containing your current material property. So if you don't want to give uniform variable right here, you just use the GL front material, and you can automatically get the material from this GL front material, which is pretty useful. You don't have to define that many uniform variable, and later on we might rewrite it, although as probably you know, everything gets outdated at OpenGL 3.1, which is not attribute variable, uniform variable. These built-in variables basically not used anymore, I believe so. So that's why I try to use not built-in material for most of the stuff. Of course I used it in here, the vertex property, but anyway, the vertex shader. Okay, and let me get the other properties. So uniform vector free, and this is diffuse, and uniform vec free, and specular. By the way, you can get this GL front material is basically a structure, so you can use the dot diffuse to get the diffuse property of the material, dot ambient to get the ambient property, and dot specular to get the specular property, or dot shininess to get the shininess property. Okay, I just want to show you that. I will not use it right now. Okay, and I need actually a floating point value for the shininess of the surface, uniform float, and I call it shininess. Okay, and let me do the same with the lighting. Actually, if I copy that, that will be a bit quicker. I will call L ambient, L diffuse, and L specular, like light ambient, light diffuse, and light specular. And again, there is a built-in variable for that, which is GL light source, and as indexing you can give what light source property do you want. For example, 0, and again get the diffuse, diffuse, specular, and ambient property for this light source built-in variable. And again, there is still that maximum 7 light if you are using this GL light functionality. So it's better to give built-in variable, because here you can give as many light as you would like. Obviously you would not make a uniform variable for every single light, but you would probably choose some better way to do it. But for now we will just use one single light and one single material for the surface, because this is obviously just the 4th tutorial. I don't want to go too far, because this program will be relatively complicated. Right, that's pretty much it. One more uniform variable. We need the light position. So uniform vector free, and I call it light as light position. We will give the light position to the fragment shader, so we know where the light is. Okay, and here let me start to make the program. So far I just give the vertex shader the position and the normal, and in the fragment shader I just define a lot of uniform variables which we will fill up from the main program right here somewhere with the obvious values, so like light position and the material property and then the light property. Okay, so let me go back here at the dia and let's see what we will need. We need the ambient first of all, so let's make an ambient. Actually this will be a vector free ambient, and this ambient will be the input, the material color times the light color, as I wrote here in this dia. So the material color times the light color, and to get that we just simply multiply the ambient, the material ambient, times, by the way, the multiplication operator in case of vectors, meaning per component wise multiplication in GLSL. Okay, so the material ambient times the light ambient. So this was quite simple. We already have the ambient light. Let me make the diffuse light again. Let's go back here at the dia and let's see what we will need. We need a vector which pointing to the light position. To get a vector which pointing to the light position, so create a vector free and vec and or surface to light. This will be the name, and again just the end position minus the start position. The end position is the light position because that is where we want the vector to point at, and the start position is actually the surface position. To get the surface position we have here the variable, this varying variable which we gave from the vertex shader. So I just pass position here, position. That's simple enough, but as I said, all vector has to be normalized, so just normalize. So I just normalize this simple vector which pointing to the light position. Perfect. We have a normal vector as well. Here I call it normal, although there is one problem with the normal, and here I will demonstrate it. So as I said, the values are interpolated in the vertex shader, between the vertex shader and the fragment shader, so the varying variables. So if one normal vector look like this and the other normal vector look like this, for a moment presume that both of these vectors are actually normalized. Then whenever I do the whenever the vertex shader, the varying variable, will do the interpolation, it will go as a straight line right here. And this is a problem because vector, for example, here at the center will be not normal length, because this is a much shorter length normal vector right here. And if I will use just this normal right here as my normal vector, then obviously I will get artifacts. Oh, by the way, I haven't mentioned that the normalize is obviously normalizing a vector. You can pass vector 2, 3 or 4 into this normalize function and it will just return with the normalized value of the vector. It is nothing new. Just I forgot to mention, because I said that the new functions and new variables and things like that I will make mention of. Okay, so I have to renormalize this vector. To renormalize the vector, I will just call simply the normalize function. Okay, so I will make another vector, vector 3, and I call it norm, not normal, and this is normalize norm to avoid lighting artifacts. So basically I just renormalize the normal vector which I gave from the vertex shader, because of this problem that here at the center it is not normal length, but all of the other vectors are actually normal length. Okay, so we have the normal vector, and what I wrote here is that actually we have to get the dot product between the normal and the light position. So let me do it. I will make a float and I call it decontribution, like the diffuse contribution. Actually decontr, to make it easier to remember, and type it. So I get the dot product between the normal vector, which is norm, and the vector which pointing to the light, so surface to light. Okay, this is basically give back a number between 1 and -1. So I will not care about the number if it is less than 0, because if it is less than 0, that's meaning that the normal vector pointing to the different direction than the light, or more than 90 degrees basically. And so I get the maximum between 0 and the dot product result. So this will pretty much mean that if it is less than 0, then 0 will be returned. If it is greater than 0, then the dot product will return. So I have a number now between 0 and 1. Pretty simple. And actually I have to calculate the diffuse light right now. So let me make another vector, vector3, and I call it diffuse. And this diffuse light will be the material diffuse times the light diffuse, because as I said, the output color is always the input color times the light color. So the material color times the light color, basically, for the obvious reason which I showed you in the first dia. And then I multiply that with this floating point variable, the decontribution. So if this decontribution is 1, then I get the maximum possible diffuse light. If this decontribution is 0, then I get black, basically. And obviously all the other color between the two. So now it is time for the specular light. Okay, so here I am, the specular light. Okay, the specular light, what vector do we need? We need a vector which pointing to the light position. We already did one of these vectors, surface to light, so we don't have to care about that. We need the normal vector. We have that vector as well, right here, the normal vector, so we don't have to care about that either. We need a vector which pointing to the viewer position, so let me create one of those vectors. So vector3 and surface to view. Okay, and the surface to view vector will be pointing to the viewer position. Again, to get a vector with pointing from somewhere to somewhere, we get just subtract the start point from the end point. So we get the viewer position, which is actually 0, 0, 0, because the camera is always at 0 position in OpenGL, and subtract the surface position, which is position. And actually I said that we have to normalize the result. Normalize it, because in order to do the dot product, or the dot product give the result which we want, we need to normalize it. Okay, one thing that if we subtract anything from 0, it will be just the minus of that, so I can actually remove this, because 0 minus 5 is just minus 5, we don't have to write 0 minus 5, so I can just delete this, and here I have the surface to viewer vector. Okay, and as I said, we need a reflection vector right here, the reflect vector. So let me create another variable for that, vector3, and I call it reflection. And there is a built-in function, luckily for that, which is called reflect. And this reflect function waiting two parameters, the normal vector, which we already have, the norm, and it's waiting for the light to the surface, so the surface to the light. So this is right here. So I pass that as well. And as I said, this reflect vector will give the -1 of this vector, so the vector which pointing to the exact same direction which we want to point, because as you can see, GLSL will waiting the vector to give like this, so it's really the reflection, but we want the vector to be like this. So to do that, we just simply negate it. We can negate the surface to light, or the result of this reflect function doesn't matter, it will give the same result. Now we have these two, so actually we have to dot product these two together. So I will make a float and s contra, like the specular contribution. To get the specular contribution, you dot product together the surface to view vector and the reflection vector. So let me do that. Dot together the surface to view and the reflection. So this will basically get a number between -1 and 1, similarly here in case of the diffuse light. Again, if it is less than 0, that pretty much means that the current phase is on the other side of the light, and according to the definition, the light doesn't shine through the material, so in this case the contribution is just 0. So again, we can use this maximum, the dot product, and the 0. So in this case, if it is less than 0, then 0 will be returned by the maximum function. It's obviously get the bigger number. Okay, and as I said, we have to get the power of that power of this result, so the power of the contribution and the shininess. I will not make a separate variable and a separate line for that, because I can put it right here as a lot of functions in each other, basically. Similarly, you can do it in C++ and shininess. Okay, so I get so first of all I get the dot product, then I get, if it is less than 0, then it will be just 0, and then use the power function to get the result of this max function to the shininess power. So for example, if the shininess is 10 and the dot product is 1, then 1 times 1 times 1 times dot 1 is returned, where there are 1 multiplication with 1. So this is what the power function does. It's again pretty simple. It is a built-in function. So this is the specular contribution. Okay, and to calculate the actual specular light, again make a vector3, and I just call it specular. And the specular will be just as simple as, again, the light specular times the material specular we get the specular together, because the output color is always the light color times the material color, where the multiplication is component wise. And then I multiply it with the contribution, so S contribution. This is pretty much it. So the output color, so here this GL frag color right here, will be just the sum of this. So I get again a vector 4, and this will be just ambient plus diffuse times specular. So we add together all of the components of the light, obviously, to get the value. And in case of vector 4, we need a fourth number, because both the ambient, diffuse and specular was vector free. It doesn't have the 4 alpha component, so I will just manually assign an alpha component right here in the frag color. And that's pretty much it about the fragment shader. The ambient is pretty simple, just the input, that's just material light times the light color, material color times the light color. Then the diffuse, we do basically what I said in the dir right here. We get the dot product, the angle basically between the two, and the greater the angle is, the smaller will be the contribution. In case of the specular, which is the last, basically we get the reflection vector, and if we are closer to the reflection vector, we are seeing a shiny point. You can try it out with, I don't know, flashlight and a mirror. So if you are in the reflection vector, then you see a very shiny point in the mirror, and if you are looking somewhere else, you just see that there is some light there, but it will not be that shiny. Right, that's pretty much it. So the last thing it's remaining to do is actually go to OpenGL and fill up all of these uniform variables. To fill up all of these uniform variables, I just use the GL uniform free F. Okay, the GL uniform free F will basically first of all get the position, which is GL get uniform location, and from the program, and the name is first of all the light position. Okay, and then the value. The value will be 0.0, 0.0, 0.0, which is pretty much the eye position. So the light will be actually on the exact same place as the eye position, as the camera. So we can test it out if we are moving in the camera. The light calculations are okay or not. Okay, by the way, if you want the light to be on the scene, so not carried by the player, you multiply the light position with the current model view matrix. The model view matrix, in that case, it will be stationary on the, so it will be static on the scene. It will not move when the camera is moving. But in that case, we have the 0, 0, 0 position, and we're not multiplying it by any matrix, so we always get the light at the exact same place as the player. Now let's fill up the material property, which is basically the color of the material. I will copy this to save time. Copy 1, and actually copy this. 2, 3. Okay, this will be the material property. So what is the ambient, which is the ambient color? This should be probably a little bit, so a small value. I will just give 0.2 for this value. It's a very dark gray color. The next is the diffuse property. This should be a little bit quicker. I will give 0.6, which is basically a gray material, lighter gray, because it has a bigger value. 1 is, by the way, the white, and 0 is the black, as you probably know. The specular property. The specular property will be, actually I will make it 1. It's a very shiny material, so it's completely 1, the specular. Okay, let me do the same with the light color. So light, light, light. To save time, I will just leave the same values right here. It doesn't really matter. If you increase the light, obviously it will be shinier. And the last one value is the shininess, which is remaining, which is just a simple floating point number, so 1f. So a simple floating point number and shininess. Okay, and this simple value will be, I don't know, make it 32. So it's a small point. The higher this value, the smaller that point will be. I'm pretty sure we are finished and ready for a try, although one thing I will add later on to this lighting calculation is actually the attenuation, which is basically if the light is get farther away, the small contribution will it have. I will do it in a moment, but let's first try to compile and run it. So here it is, I'm compiling, and then let me try to run it. I can't guarantee that it will work, and indeed it's not really working as I hoped that it would. Maybe, I'm not sure about that yet. Let me make this shininess value a little bit smaller, for example 10, and see what happens then. Okay, I find it a little bit of problem here in the reflect. actually it seems that it doesn't really matter the order of the parameters. I always thought that it doesn't matter if you put the normal first or the surface to light vector first, but actually it does matter. So I changed the order to the light to the surface. Actually, it's the light to the surface to the light, the vector, and the normal vector. And now if I run the program, it does actually work. This was all which I actually screwed up. And as you can see, here is the specular light. I changed it a little smaller value in testing, but actually it's a good way to try what difference does it make if I pass a greater value, a bigger value. So I changed it from 10 to 32, and you can see that the result is that indeed it's a smaller specular point right there. And by the way, you probably noticed that this is just 4 simple vertex, but still we get a very nice result. So here is, I can move, I can bring the camera anywhere I want, and it seems okay. Now the only problem is that if I am going farther and farther away, finally this specular light will be everywhere basically. So it's really unreal, because as we get farther away from something, we basically get smaller and smaller specular light. So let me do that right now. The fixed functionality uses the attenuation. I'm not sure if I can say that word. It's basically a simple floating point number, so I can make it right here, float, and I just call it ATT because I can say that word. And this is just a simple number, 1 divided by something called constant attenuation, right? So this is 1.0 in so it's basically, if it is just 1.0, then it's basically nothing. Then we get the distance, and this is the linear, and so we get a number, I don't know, 1 times the distance, so d. Actually, let me get the distance right here, so float distance, and the distance is actually the distance to the position. So distance is actually the length of the vector to the position from the vector from the light position, so light position to the position, right? So light position, light pos. So we get a vector which pointing from the current position to the light position, and I get the length of it. If I am correct, the length is basically giving the length of a vector. Okay, so I get the length into this floating point distance variable, and then this is the linear, and there is another one called quadric. So again, you can pass some values right here. I don't know, I just pass 1.2 everywhere, and this is distance times distance, so this is the quadric. And this is the factor which the light is basically get less bright. So I just multiply the end result by this ATT variable, and if everything goes correctly, then as I go farther, the light will get less shiny. I'm not sure how much, but it seems that it's way too much, as you can see. So in order to resolve that, basically I just use smaller number right here, so 0.1 instead of 1, for example, and 0.01 or whatever, like this. Okay, so again, just play with the number until you get the result which you want. You don't have to recompile the shader, and as you can see, now it is less shiny, and as I go further, it's basically get dark, very dark. That was pretty much the lighting. By the way, if you are using textures, the only difference you have to make is not using the ambient and diffuse material color, but use the current pixel color which you have get with the texture to the function. Pretty much that's it. By the way, if you have multiple lights, then just go through all of the lights in your scene, and then add together all of the lights ambient, all of the lights diffuse, and all of the lights specular property to a variable, and then assign that variable right here. So I don't know, if you have more lights, then you just use for int I equals 0, I less than the number of lights, and go through all of them if they are in a array or something. And there is another kind of light, the flashlight or spotlight, as it is called in GLSL. This is not so complicated, but I will not go over that. Basically, all you need to do is get the vector, which is basically the direction of the spotlight, and then get a vector, which we already have, a surface to light vector, use the dot product to get the angle between them, and use a variable. So for example, if it is less than 30 degrees, the angle between the two, you only apply the rest of the calculation to that. If it is greater than 30, so it's basically out of the cone of the light, then you don't have to do anything, you just set it to black or get some ambient light or something. I think I will finish it right now because I forget to talk if I talk that much. So I really get tired upon this tutorial, so thank you for watching and have a great I knew that I forgot something, and to make a demonstration that it actually worked for other objects as well, so not just a simple quad which I had here, but actually complex object like this monkey object. I just quickly included this object loader which I wrote earlier and loaded a monkey object, which is basically just, you know, Blender, and then create a monkey. And actually I created two. One is the low definition. This is what the default definition is, so without any multi-res or something like that. This is just the default. And by the way, I activated the smooth normals, the vertex normals here to true, because obviously it looks better. Mostly with per-fragment lighting. It doesn't look that much better with just normal lighting. And now if I run this, as you can see, if I move a little bit further, it's pretty nice actually. This is the lowest possible definition for this monkey object, and it looks kind of cool. But if I load the monkey object, which is not the low definition, but I only added one single multi-res. So here in the Blender I added one multi-res, which is not too much. With the fixed functionality lighting, about 3 multi-res was needed to make it look about okay, but I only added one single multi-res, and as you can see, this is almost perfect. Okay, I don't say it's perfect, but it's very close to be perfect, and it's work if I go here at the bottom or somewhere else, so it's working in all cases. And yeah, I just pretty much cut this to the end, so you can see that this lighting model will actually work any kind of model with any kind of model, any object. So it's a pretty standard way of lighting, which is by the way the same as in case of the fixed functionality, except I will do it manually, and I will do it for every single pixel instead of every single vertex. So now thanks for watching and have a great